Okay, so welcome to lesson 26 on electric circuits. Today's discussion is going to focus on resistors that are connected in series. So you should know by now that there are two ways that you learn about that resistors can be connected in. That is, resistors can either be connected in parallel or in series, right? And for today's lesson, this is going to be our main focus, resistors that are connected in series. The next lesson, that's when we're going to talk about resistors that are connected in parallel so that you can actually be able to distinguish between the two. So to start off that discussion, I want us to first define Ohm's law. So how do we define Ohm's law? So Ohm's law says that the potential difference across the conductor is directly proportional to the current through it. So the potential difference or current is directly proportional to the potential difference through the conductor, provided that the temperature is constant. So I'll say provided that T, which is temperature, is constant. So that is basically saying that current through any conductor is directly proportional to the potential difference, provided that the temperature is constant. So we know that the symbol for current is given by I there, and it's measured in amperes. And current, we were introduced to it in grade 10. They said that current is nothing but the rate of flow of charge. So it's given by this ratio here, Q divided by T, where Q is measured in coulombs, C, and T is measured in seconds, right? That's the SI unit. And potential difference, we know it to be the work done per unit charge to move that charge from one point to the next, and that is given by this ratio over here. So of the work done per unit charge. So this is the work done. We've already spoken about work. It's measured in joules, and then our charge is measured in coulombs. So those are some of the important things to know. But the one equation that we are mostly familiar with is this one, I equals to V over R, where this is our resistance, right? And this is normally called Ohm's law. And normally some people would write it this way. It's the same thing, V over I. So maybe this is what you are most familiar with, but it's basically the same thing. Remember, like I mentioned, this is the resistance and it's measured in ohms, or just that Greek letter omega there. So that is just a few important things. I don't want to discuss way too many things that are not necessarily important right now. So now I want us to talk about properties of resistors that are connected in series. So let me try to draw a circuit diagram quickly. Okay, so imagine that you had a very simplistic electric circuit diagram like this one, where you had a battery. So this would be the positive terminal, this would be the negative terminal of your battery, meaning current, conventional current at least, would be flowing in this direction. Let's call that current IT, right? And then, so you see how our this one is a voltmeter V with a circle, to show that it's a voltmeter, and it's always connected in parallel to whatever respective device it's attached to. So another thing to note is that there's actually no current flowing in this voltmeter over here, and then your conventional current, like I mentioned, would be moving from the positive terminal to the negative terminal. Then we can follow that current. Remember, it follows and it goes through resistor R1. And then we would find that the current here supplied by this battery here, IT, would actually be the same current that we find here at I1. So IT would actually be I1. So it will be the same current, the same thing here. We'd find that IT, the same current that was supplied, is the same current that we measure through this resistor I2. Same thing. I think you see where I'm getting to. So it's the same current up until there is our current. So we're just following our current in this scenario up until it reaches the other side, and then you have a closed circuit. So like I mentioned, there's no current flowing in your voltmeter, so you don't need to concern yourself about that. All right. So what is that telling us? That is telling us that resistors that are connected in series have the same current. So you can say same current flowing through them as the total current, right? All right. So this means that IT, the current, the total current that is supplied by the battery, is the same current that we're going to find at resistor 1, at resistor 2, add resistor 3, depending on how many resistors we would have connected in series, right? So that is an important thing to note. But now let us look at voltage. What about the voltage? So let's say this current here supplies a voltage. So this voltmeter here connected across your battery will actually measure the total external voltage. You'll know why I'm calling it external voltage. So let's just say it supplied an external voltage of, I don't know, 12 volts. So if we were then to measure the voltage here as well as the voltage here and the voltage here, we would find that if we add these voltages together, they would actually give us that external voltage. So what do I mean? I mean that V external will actually be V at 1 at resistor 1, V at resistor 2 plus V at resistor 3. So this resistors would split the current, would the voltage. We call them potential dividers. So they would split the potential. So they are called potential dividers. So that is an important thing to know. So let's say, for example, if this is 12 and then all of these resistors were the same size, let's say they were I don't know, 2 ohms each, and then each voltmeter would actually read a reading of about 4 volts, 4 volts, 4 volts. So it's 4 times 3, which will give us back the value of 12 volts. So this is just another important thing. The last important thing to know about resistors that are connected in series is that we can actually just reduce all of them to one resistor. So we can just say, call that resistor Rs, and we say that Rs will have a value of the value for R1 plus R2 plus R3. So you should be noticing something. When resistors are connected in series, the more we add, the total resistance will actually increase. So those are important things to know, that the current is the same through all of these resistors that are in series, but then they share the potential. And then if you were to almost like reduce all of these resistors into one, the value of that one resistor, that series resistor, would be given by the sum of all these resistors that are connected in series. So let us now move on and try to actually do a problem. Okay, so this is a diagram that is given to us. They saying that this battery supplies an external voltage of 12 volts, and then we have an ammeter, you see. So you say this is the positive, this is negative, this is the direction of the conventional current. Let's call it IT. So we have current flowing from the direction through your ammeter. So remember, ammeter allows maximum current to flow through it because it has zero resistance. So it will actually measure all of the total current, and it's always connected in series to your battery, if you notice that. Okay, cool. So now if that current, it comes through here through resistor R1 as well as through this resistor R2. So there's no current flowing here because the voltmeter has a maximum infinite resistance, so it doesn't actually have any current flowing through it up until it goes again, and then your circuit is just complete. Okay, so now these people are asking us to determine the reading on, or to calculate the reading through ammeter. It's not A1, it's just ammeter A, and then the reading on the voltmeter V1 and V2. So now we have to use everything that we have learned so far. Remember, our resistors are actually in series. So let's start with my other board. I don't want to wipe that. So let us start here. So we're saying that the current that will flow through this ammeter is the total current, right? So we can call that IT. So IT, that is what we're looking for. And then we're going to be using Ohm's Law to do this. Remember, Ohm's Law says I equals to V over R, right? So we're looking for IT, and for IT, we use the total voltage supplied. I don't want to call it VT. I just want you to actually always use V external, because you will see when we talk about internal resistance why I am quite specific about calling it external, right? So that is just the total voltage for the external circuit, and then you also divide it by RT, right? So I'm looking for the total current in the circuit. If I was looking for the current here, I would only use maybe I1 equals to V1 divided by R1. So because I'm looking for the total, that's why I'm using the total current, or the total resistance, as well as the total external voltage. I hope that is making sense. All right, so do we know what our V external is? Yes, we have that. RT, do we know it? Nope, we're not given it, but we can calculate it because the resistors are connected in series. We can find RT, which is equals to R1 plus R2, right? So that is just 2 plus 4, which is 6. So to find IT, meaning that we can just say V external, the total external voltage, we said it's 12. So we have 12 volts divided by 6, which is going to give us 2 amperes. Remember, current is measured in 2 amperes. So now we've actually found what the total current is. And you saw, so for this, don't forget to include your ohms. So it's 6 ohms, our total resistance. And the second question was saying to us that we should calculate the reading on voltmeter V1 and voltmeter V2. Okay, so how do we do that? So this is A. So how do you think we do that? So we also start with our Ohm's law, which says maybe R equals to V over I. But we're looking for voltmeter V, the reading at voltmeter V1, which is meaning we're going to use the resistor R1 as well as the current I1. But what is it that we know? So we can just rearrange this equation over here and write it as V1 equals to R1 multiplied by I1. So it's just a matter of cross multiplication. Okay, so what do we know? Do we know what R1 is? Yes, we know it. It is 2 ohms from our sketch. Do we know what I1 is? In a way we do, because remember we said for resistors that are connected in series, the current is the same, meaning the current the total current will also be the current that flows through the resistor, the first resistor, as well as the current that flows through the second resistor, which we found to be 2 amperes. Right, so now it means that it's a very simplistic calculations. We can just substitute everything that we already know. So R1, we know it's how much is R1? We said it's 2 multiplied by 2, which is going to give us 4 volts. All right, now we can do the same thing for for the second resistor. We have to find the potential difference through that resistor. Right, so a matter of rearranging everything else. So R2 multiplied by I2. We already know they are connected in series, so the current is the same. R2, the value of R2 is 4 multiplied by 2, which is going to give us 4 times 2 is going to give us 8 volts. So hopefully you are able to see how we got to that value. But this is not really the only way you can do it. There are many ways to kill a cat. It just depends on what you essentially prefer. But before I go on explaining that, I want you to notice something. So now we said that V external for resistors in series would be nothing but V1 plus V2, and we already found what V1 is. V1 was 4 plus 8, which gives us 12, which is that value there that we were actually given in our circuit. So you actually see that this law is correct. But now let us try another method of finding the what is it, the reading, the voltmeter readings, without having to use Ohm's law. So another way to find that would actually be to use our ratio. So we would say that the ratio of the resistor R1 to R2, remember the value of R1 is 2, so it will be 2 is to 4. But we can simplify it further and say that divide both sides by 2, then we have 1 is to 2. Our resistance, according to Ohm's law, is directly proportional. So they are proportional. If this one increases, this one will increase. This means that the potential difference for the ratio of the potential difference at resistor 1 would be V2, would nothing also be 1:2. But then why is this important? So if we have now figured out this this how they relate to each other in terms of their ratio, how are they proportional to each other, we can actually find V1 by saying, okay, let's take the total, which is our V external, multiply it by one part of V1, so it's one part, divided by the total parts of our ratio, which is 1 plus 2. This is this. So that actually gives us 12 multiplied by 1/3. And as you know, it's going to give us 4 volts. Doing the same thing for V2, you can say, okay, V external multiplied by the two parts of resistor R2 in terms of the voltage. So it's 2, and then divided by the total parts, which is 1 plus 2, which is 3. And okay, so we have 12 multiplied by 2/3, so that's 24 divided by 3, which is equals to 8 volts. So you see, we still arrive at the same answer, and the total V external is still equals to 4 V1 plus V2, which is 4 plus 8, and it gives us the value of 12 volts. So you can either do it using Ohm's law, or you can actually just use how ratios in terms of how they are proportional to each other. And this brings us to the end of this lesson.